Mayo Clinic presents
Emergency Medicine Grand Rounds.
Hello everyone. Thank you for tuning in for Mayo Clinic Emergency Medicine Grand Rounds, a subsection of the Always On EM podcast. My name is Venk Bellamkonda. You may know me as one of the co-hosts of the show. I'm also Chair of Education for Mayo Clinic Emergency Medicine. I'm really excited to introduce to you all a wonderful presentation that we experienced from Dr. Brian Patterson at the beginning of March 2022. Before we go further, if you are a returning listener, thank you so much for coming back. If you could, take a moment to like, subscribe, or comment about our podcast on whatever platform you are using. Each of those engagements really help extend our reach so that we can spread high-quality information further across the globe. If you are new to the podcast, thank you for listening. I hope you'll check out not just this episode, but several other pieces of content that we offer. And at the end, I hope you too will be motivated to like, comment, or follow us on whatever platform you're using. Let me tell you about Dr. Patterson, because he's pretty amazing. Dr. Patterson is a graduate of Penn State University with a degree in bioengineering and received his medical education at Northwestern University's Feinberg School of Medicine. He completed emergency medicine residency also at Northwestern University and served as chief resident in his final year. He is board certified in both clinical informatics as well as emergency medicine and is currently assistant professor in emergency medicine at the University of Wisconsin with affiliate appointments in industrial and systems engineering as well as biostatistics and medical informatics. He is author of 45 peer-reviewed publications and was previously recognized as an Academy of Geriatric Emergency Medicine Spotlight author. He serves as a reviewer for several journals with focuses including emergency medicine, public health, informatics, and geriatrics. He has led efforts at UW to create and implement a novel program which automates screening and referral for falls and fall prevention services during emergency department visits. During this presentation, we were super excited to hear from him about how he was able to integrate automation, data, machine learning within the goals of improving the care that we deliver every day and optimizing overall public health. With that, let's give the Always On EM podcast floor to Dr. Brian Patterson.
Well, thanks so much for that great introduction. So, as you heard today, I'm going to be talking about predictive analytics to prevent falls after ED visits. And just some quick disclosures, none of which are particularly relevant to this talk. I've done some work on COVID diagnostics and have grant support from the HRQ, which has supported the work that I'll be talking to you about through the grant mechanism. So as you guys heard during that excellent introduction, I wear a couple of hats at UW. I mostly think of myself as a researcher in informatics. But I've increasingly also taken on a role using predictive analytics within our health system. And I've worked on this project in both roles. My goal in this talk is to tell you a story about our efforts to prevent falls after ED visits at UW. And then along the way, weave in some more general information about both falls prevention and then the development and implementation of predictive models. It's always a bit intimidating to give this talk. I'm going to be moving across a number of domains, and I'm fairly certain that many of you in the audience are more expert than I myself in each individual area. So hopefully where I can add some value is by giving you this sort of big picture narrative arc of how all these different disciplines could fit together. And I'm going to talk a little bit about my own journey on multidisciplinary teams throughout the talk. Back when I started this work, which was now probably 6 years ago, I was really excited, a little bit sooner out of residency, really excited about gaining training and becoming a data scientist and doing a lot of work in machine learning. So I'm really excited about using machine learning to improve patient care. And what I thought was I was going to have like a data science lab and be, sitting around writing code and that sort of thing. And what actually happened was that I got the chance to collaborate with great partners who actually do that kind of work in computer science and do a little of it myself. But I also got training and collaboration with partners in informatics, in engineering, our human factors engineering department, and also in quality improvement. And so the sort of hardcore data scientist I thought I'd be only ends up getting like a couple of slides in the following presentation. And now I see my expertise not in any one of those domains, but hopefully in the ability to interact meaningfully with experts along that developmental arc to drive a project forward and keep it relevant to our clinical practice. Now, I've given versions of this talk to several different audiences, but I'm always excited to talk to an academic clinical emergency medicine audience. And I think it's often clinicians, it's tempting for us to think when we're faced with some of these informatics innovations, like, why not leave this stuff to the IS teams? And hopefully what I can demonstrate is that when we as end users get involved, things get much better. Often clinicians I meet are a little skeptical about artificial intelligence or machine learning and their impact on healthcare. And I think that's understandable, but I'd encourage you all to take an attitude of engagement towards these technologies. I think it's clear from my standpoint that they'll all be radically changing our practice moving forward. And I'd much rather it be forces within clinical medicine that are driving that change rather than us later down the line interacting with external actors who are imposing these technologies upon us. So I'll get off my soapbox and get into the talk. So because you guys are a clinical audience, I get to, start off with a case. So this is an ED case that's kind of like a composite in our emergency department, very common. So let's say we see a 78-year-old male who presents to the department with the chief complaint of a fall. It was witnessed by his wife, who says he tripped over a rug and fell on his sideways, landing on his side and then striking his head. And now he's got hip and head pain. And you'll note he's got atrial fibrillation, is on rivaroxaban, and he's taking terazosin for BPH, which may have contributed to this fall. Now, at least at the University of Wisconsin, that fall on blood thinners is going to be a trauma activation. We're going to do a big workup for this guy. And, not surprisingly, we find that this patient has a hip fracture and a small subdural hematoma, which those of you in the audience who have seen these types of injuries and follow these patients know that for a 78-year-old male, this is a morbid set of injuries. This gentleman's going to be very lucky to get back to the quality of life he had before the injuries. Both of these have the potential to significantly derail his recovery. And it wouldn't be that surprising to look in this guy's chart and see that 7 weeks ago, he was seen in the emergency department after a low-speed motor vehicle collision. He had negative x-rays and a head CT, then another trauma activation, of course, but he hasn't followed up since. And we see these patients over and over. The question that I started to ask at the beginning of this project was, could we do anything at this first visit to prevent the second visit? And so why should we identify fall risk in the emergency department? Why is it our job as ED clinicians? And I probably don't have to tell you guys that falls are a huge problem. They're greater than 3 million ED visits per year. They're the number one cause nationally of geriatric traumatic morbidity and mortality. And unfortunately, Wisconsin leads the nation in fall-related deaths. If you look, Minnesota is not much better. It's kind of like an upper Midwestern problem and a New England problem, and this is fall-related deaths among the elderly. So it's not just that our populations are older, but even among older adults, we have a higher rate of injurious and deadly falls than other states. In my shop at University of Wisconsin, almost 25% of older adult ED visits are falls related. And at UW, if we look, we see that a third of the patients that we see in the ED for a fall were seen in the 6 months prior to falling for either another fall or for something else. After an ED visit, we know that patients are at an increased risk of falling from their baseline, just due to any type of deconditioning they may have from whatever brought them to the ED in the first place, or possibly the ED visit signaling some poor care trajectory. And we know that as a hospital system, we have fall prevention services available. But before we started this project, we really didn't use these that much. And that's understandable. We're not trained necessarily to assess for fall risk in the ED, and it doesn't seem like part of a patient's acute care visit to refer them for fall risk reduction, especially if they're not there for a fall in the first place. And so I see fall risk as sort of emblematic of a larger problem, which is how do we improve public health from the emergency department? And there's a tension here, right? Because we all know that we have a huge opportunity to influence care trajectories for patients who present to the ED, especially true for older adults. These are patients who, our population may not be getting care elsewhere in the system at the same rate that people coming into a primary care clinic may be. Our ED visit may be like a particularly influential touch point to influence the care trajectory. And there is a new momentum in this area. I think with the rise of social emergency medicine, more and more emergency physicians really see it as our mission to improve the care that our patients get, not just in the ED, but connecting them to resources after the ED to improve their care. But the constraint is that any one of these public health initiatives is going to take some time. And anytime we want to do one of these sort of extra things for a patient, we're going to have to balance that against the people that we have in our waiting room and against our core mission to, provide acute care. And there are lots of other noble causes that we know we should be screening for. I'm sure in your emergency department, every patient's getting screened for suicide risk, alcohol risk, domestic violence, things we don't want to stop screening for. But at the same point in time, how do we decide what is the right package of screening to give a patient when they come to the ED? And how do we minimize that burden on our other, on our main goal of providing timely acute care for every patient who walks through the door? So getting back to falls, at the UW, we have a mobility and falls clinic. So this is a one-time multidisciplinary visit where a patient could be referred after a primary care visit, after an ED visit, anytime that their providers want them to go, this clinic is willing to see patients. And at this clinic, a patient sees a physical therapist to talk about gait, nurse, case manager who could talk about home safety, things like that area rug in my case. And they see a provider who's going to work with them on medical reasons why they might fall, like perhaps deprescribing that terazocin. This type of multidisciplinary intervention has been associated with a pretty good relative risk reduction in falls. In a now very old study, one of the first to look at this kind of thing, specifically after ED visits, found a 40% relative risk reduction in falls. The falls literature is actually a little bit mixed if you look at it. Falls prevention from primary care with these types of multidisciplinary interventions is controversial. Every time it's been studied from the ED, it does seem to work. And more recent studies, including the recent GAP Care trial, have shown that the ED may be a particularly effective place to prevent falls in the future among our older adult patients. And so at the start of this intervention, I approached this clinic, and luckily they were really excited to get ED referrals. These geriatricians who run the clinic are on the same page as we are about the importance of falls prevention. But one very reasonable concern they had is like, we already have a clinic that's operating pretty well. There's a way to get there. If you guys just start like referring patients from your very large and busy ED, are we going to get overwhelmed and not be able to provide the care that we want to our patients? So they said, is there a way we could pilot this and get let's say 5 referrals a week and see how things go, which I think was a very reasonable ask, but it gives us a very distinct project that we have, which is not to increase fall referrals, but to give 5 slots per week filled up with our fall referrals. And how do we fill those slots with the patients who are going to derive the most benefit? So what we need is a screening program that picks the 5 patients who are most likely to fall in the upcoming next 6 months or so, and give those patients the referrals to Mobility and Falls Clinic. And I want to do this without becoming the most hated person in the department. So my goal is to do this with no new questions or tests. There are a lot of validated falls screening tools that involve like a functional test like Get Up and Go and several questions. These things have good predictive ability, and we could have implemented something like that, but they take a lot of time, like 5 minutes, which is pretty significant for all older adults presenting into the emergency department. And so the question was, what can we do to use the informatics to do things better? And the strategy here is we already know a lot about these patients. These are older adults, and for patients who are eligible for referrals to our falls clinic, we're talking about in-system patients. So we're always complaining that these patients have 1,000-page long charts anyway. Can we use that data, risk stratify older adults for risk of fall automatically without adding to provider burden? And then use that data also to right-size our intervention to draw a threshold and only refer those patients who are at highest risk for falls. And all of this is moving towards the concept of a learning health system, which is the way that I sort of have framed this intervention from the beginning. This idea that how do we shorten the loop between research and practice in our health systems, use the data that we collect clinically normally for patients to improve the care of our patients in a smaller loop than just a secondary review of data for research, getting that research out there, having somebody else read the paper and then operationally start it. How do we shorten that loop and start to use real-time data that we're collecting from our patients to improve care at our institution? And the way the sort of modality that I wanted to use coming into this, because this is what I was interested in, right, is this idea of machine learning. And what exactly is machine learning is a question that I get asked quite frequently. So I would define machine learning as any algorithm that builds a model based on sample data, which I'll also refer to as training data, in order to make predictions or decisions without being explicitly programmed to do so. And there are a lot of different ways we can build these models, which I'll talk about. But this idea that we're training the model in training data and then using it in some other data to make a prediction is, in my mind, what makes a model a machine learning model. And there is a lot of promise to these models. When I started this, I would say, I don't know how many of you are familiar with this Gartner hype cycle. This is something that people talk about with the diffusion of new technologies. But I would say I started this work 5 years ago, probably close to the peak of inflated expectations for machine learning technologies. The idea was like, we're going to use these technologies to totally revolutionize medicine. We're going to get this thumbprint look at the data on each patient, be able to make fantastic recommendations. And this is always the best time to write a grant to support this type of work. But I think we've since slid down, and this graph is overly simplistic, but I think some of the pitfalls of machine learning have come to light over the past few years and are important to address. Like any new technology, this thing has its ups and downs. And some areas people worry about when introducing machine learning technology is, one, its generalizability. Does a model that I use at the University of Wisconsin, is that going to work at other sites if we translate it to another site? And because of the way that these models are trained, they're highly dependent on the way the data is stored within a system. So there are very real concerns with how well they translate from one center to the other. Another concern is explainability and causality. Machine learning, for the most part, and there are people who work on causal machine learning now, but most of the time when you hear about these technologies, we're explicitly looking at finding the association between a set of predictors and an outcome, assuming that association is going to maintain over time. We're not necessarily saying that the predictors we use cause the outcome. And that's important for a couple of reasons. First of all, it can have implications on patient and provider trust in these models that have a lot of inputs, are sort of black boxy, and may not fit with the kind of model of practice or medical thinking that people use coming into a problem. And whenever we're looking at just associations without causality, we need to be really thoughtful about the way that models can incorporate biases that exist in training data or exacerbate disparities that already exist based on how they pick those up. So these are all kind of pitfalls that we need to think about as we put machine learning models out there. In terms of types of machine learning algorithms, this is one of those slides that I thought was going to be like my whole Grant Rounds talk 5 years ago that we go through pretty quickly. People use a number of different algorithms that fall within machine learning. Probably the most commonly used algorithms are still regression algorithms like linear regression, logistic regression, and then some fancier regressions like lasso regression and ridge regression that have some penalty terms that are probably outside the scope of this talk. People often ask me, how do I know if I'm using logistic regression just to do a logistic regression like we've been writing about in the medical literature for 30 years, or I'm doing it in a machine learning format? And I would say it's about how that model is used. If I'm doing an epidemiologic study where I'm looking at which factors are associated with fall risk and I put them all into a logistic regression model, I'm not necessarily using it to do machine learning. I'm fitting a model to the data. If I take that data and divide it into training and test data and do that fit of a regression model on my training data, and then use that to make predictions on my test data, then yeah, I'm doing machine learning with a regression model. As I said, regression models are very commonly used. We also use models based on decision trees, which are classification trees, and sometimes a large number of different classification trees can be built. These are what you hear referred to as random forest models. Gradient boosted models is a term that just refers to the way in which these models are fit. And you can use gradient boosting to change the way that we fit regression or decision tree based models. A gradient boosted decision tree model that you often hear about in the medical literature is XGBoost. That's one of these gradient boosted models. And then we have support vector machines where we do a little bit more modifying of the variables before we fit a model. And then deep learning machines, or which you also hear referred to as neural network, where we're creating a set of encoders that work maybe sort of like human neurons that we put in a large network to try to help the computer learn and make decisions. As we kind of go down this list, we go from models that people in medicine conceptually understand well, where you can see how the inputs make the outputs, down to a deep learning model, which is very black box in terms of even when you're training the model, you don't really know how it's making the decisions that it makes. A common strategy, which I employed here, is I've always been told, just use the simplest one that works well. And if you don't need to use one of these fancier ones, don't don't do it. So you'll see we went in this project through gradient boosted models, and luckily we had the performance that we were looking for. So we didn't need to wade into this world of support vector machines or deep learning. And one thing that I've learned is that getting a model that works is often what we're focused on, but it is not what is going to change patient care. And so I've tried to move my thinking from talking about machine learning models to talking about predictive solutions in healthcare. Where we talk about a good analogy here is the movement from paper maps to Google Maps. If you look at the model that runs Google Maps, there's a machine learning model that predicts how long it's going to take and what the best route is. It's not very useful in and of itself without a really slick interface that tells you where to turn as you're driving. And it's similar as we look at using machine learning data in healthcare. If I'm going to predict who's going to fall down, just telling providers their patients may fall may not be all that useful. We need to put our model into a place that's integrated into the workflow. And that's where we start to work with engineers and design thinkers about, and clinicians, very importantly, about like what is clinically actionable information and how do we get that to the providers. We want things that come in at the right time, in the right venue, in the right format to inform provider decisions and actions. And certainly I am not the first person to have used predictive models in healthcare. There's a long history of people using predictive models to try to influence practice. And around the start of the 2000s, when there was a lot of excitement around artificial intelligence, a heuristic that took hold that is potentially damaging is this idea of looking at these models like crystal balls. No model is going to be perfect. And in fact, getting a model that's even as good as like a clinician gestalt in most situations is pretty tough, right? So the idea that we're going to have a model that's going to tell you better than your own assessment as a physician whether this patient's going to fall or not is a really high bar. And when we set a model up as saying this patient's going to fall down, you should refer them, or we think this patient's safe, they won't fall down, that crystal ball mentality leads to, first of all, wrong decisions being made because providers disengage from the decision-making process. And second of all, it's one of the big things that erodes trust from the providers, because your crystal ball is great if it's always right. But in a world where nothing is perfect, when you get a recommendation that you know is wrong, you're going to lose trust in a model if you think of it as a crystal ball. So as we put these models out there, we try a lot to talk about models as not crystal balls, but co-pilots. You want the interaction between the human and the computerized system to be one where you're hearing like, hey, from what I can tell, digging through this patient's 1,000-page chart, they're at pretty high risk of falling down. Do you want to refer them to the falls clinic? And then the provider to say something like, I hadn't really been thinking about fall risk in this patient who's coming in for generalized weakness, but that's a really good idea. We should refer the patient. Or this patient is, in memory care already, and all the fall risk stuff that could possibly done has been done. And yes, I know he or she is very likely to fall down, but I'm not going to refer them. Thank you very much. Those types of interactions with a predictive model are more healthy than looking at it as a crystal ball, and can provide more engagement and more trust. So this was one of the things that we explicitly tried to do with this, is how can we build this as a co-pilot as opposed to a crystal ball. That was kind of some background on the theory of machine learning, what we're trying to do, how we're trying to design it. And now I'm going to take you through like how do we actually start. And I just got done saying like it's not all about the model, but you definitely need a model to get started, right? You need to know, is this possible? And the way that most people do it, that I did it, is look at retrospective data, right? So we took a look at electronic health record data from all our visits in the system, patients age 65 years and older who visited our ED. We took about 4 years of data. We found patients who met our eligibility criteria, people who are seen in the ED and discharged over age 65 and have a UW primary doc, which is important for a couple of reasons. First of all, we only want to provide falls referrals to patients who are eligible to go to the referral, because it would be very frustrating to get referred. And second of all, patients who have a primary doc in our system and are over 65 are quite likely to be seeing that primary doc fairly regularly and to have that big chart. If you are somebody who's visiting UW to see your, grown son or daughter from the Twin Cities, and you don't have any information in our Epic, some of the data features that we use may not be populated, and our model may not make as good predictions. So it's also sort of a data sufficiency standard in this case. And our training target, like what does this model actually predict, is not all falls, because we can't measure falls at home. They're very poorly reported. We didn't have an army of people calling every patient over 4 years to see who fell down and who didn't. But what we're looking at is ED revisits for falls within 180 days of an initial visit for any purpose. And the reason we chose ED revisits was, one, because it's cheap and easy to measure, but two, it's also an outcome that it's easy to argue that that's something we should prevent. Like, that's not just a fall, that's a morbid fall. Like, you had to go to the emergency department for it. And when we think about like the return on our investment for whatever process we're making, what we want to say is we want to do this many things to prevent an ED revisit for a fall, rather than just preventing a fall. So that's what we're looking at. If these numbers look a little bit low, they still look pretty high to me. So what we're saying is anybody who comes to the ED for any reason, they have almost a 9% rate of returning within 180 days for a fall to our emergency department. They have a much higher risk of actually falling down if you were to go out and check. So when we look at potential predictors, there is in machine learning sort of a temptation to use this like real kitchen sink approach, right? Like, let's just take all the data in the EHR. Like, the more data the computer has, the better. And that process may get you the best metrics up front, but it can be problematic on the back end when you have some model that you're trying to like sell to physicians that says like, hey, people are likely to fall if they're, like mean corpuscular hemoglobin is low, or they're, like weird lab values start coming up, and you find these like strange. So you do want, like, you don't want to say that your model's causal unless you've like made good and sure that it's causal. But at the same point in time, things that couldn't possibly cause a fall, you probably shouldn't have in your model. And to take a broad view, we use this explicit model. There's called the Anderson model of healthcare utilization. It's very common in health services research if you haven't seen it before. But it talks about all the reasons people get injured and seek care for getting injured. And what we did was we took a look at all the features we had in our EHR. And if we could put them in one of these 6 buckets in this graph, we kept it. So we ended up with like 725 features that we used in our research data set. So it's like a lot of things about prior healthcare utilization, a lot of demographic factors, a lot of information about the ED visit itself in terms of vital signs, diagnoses that were assigned. Only things that are available while the patient's in the ED, however, because that's important when we go to implement it. And then we train models on this big set of predictors where we know the outcome in retrospective data. And this is all that technical stuff I thought I'd get to learn, and what I thought I'd be talking to you about, quite a bit. And as you'll see, it's like 2 slides. So first, we have to clean the variables to make them work in the model. I put this bullet up here not because I want to talk about variable cleaning in this talk, which is really boring, but I do want to mention that it's like 95% of the work in doing one of these projects. Running the model itself is as simple as, unless you're doing some sort of cutting edge machine learning, the off-the-shelf model tasks are pretty good. And having anyone who knows a little bit about how data analytics work, you can get up and running and start making predictions using machine learning models from a data set quite quickly. One important part is choosing a test train split. How are you going to split your data, and making sure that the data you're reporting as you tested your model on has never been seen by the model before. It's very easy to overfit a model and get a model that works extremely well in training data, but then doesn't work at all in the test data. That's the one that starts to pick up on like really random associations within your data. And so that's one of the big dangers of machine learning, is overfitting. And anytime you're evaluating machine learning data, you want to say like, okay, what was the training data? What was the test data? And was there a real wall in between this data before the model was tested? So we ran a bunch of models, and then we have to evaluate them. And when you run one of these models, the output, no matter which type of model you run, you can output it in a probability of the outcome, right? So you have a bunch of data that goes in, and it spits out for a given patient visit at the ED, what's the probability that this patient's going to fall in 6 months? And then probability is nice, but you want to set a threshold, right? For when are we going to fire this thing? So every time you set a threshold, you create a 2x2 table. And I don't want to belabor this too much because all of you have probably seen these many times. But the idea is, like, once we have a 2x2 table, we have a given model at a given threshold has a set of test characteristics, a sensitivity and a specificity. And if we move that threshold, vary it from, let's just refer everybody and say everybody's going to fall, you're going to have a model that is 100% sensitive because it catches all the falls, but has no specificity because it says everyone will fall. And then as you go back through those thresholds, 100%, 90%, 80%, 70%, 60%, down to 0%, you'll have a model that's extremely specific. It never has any false positives because it doesn't tell anybody they're going to fall. And as we move that threshold through and draw this sensitivity versus, in this case, it's 1 minus specificity, we get the ROC curve that you guys are probably familiar with. And we can measure the area under that curve and talk about how good a model is overall in discriminating for falls using that curve. And it's important to remember when looking at these numbers that the range is 0.5 to 1. So 0.5 is like a really bad model. It's no better than a coin flip. 1 is a perfect model. People say, like, if you're over 0.6, your model is operant, that it's doing something. If you're over 0.7, probably doing okay for many healthcare applications. And so we generated one of these things in our retrospective data, right? And this is where a lot of machine learning work gets to, right? Like, it answers the is this possible question. And I would say that the answer, if you look at our models, we're getting things in like the 0.78 range, which is pretty respectable. It's nothing to be like, we can predict every patient who's going to fall down perfectly, but it's enough that it's good enough to publish. But it doesn't really get me anywhere near the question that I had, which is how do I pick the 5 highest risk patients and send them to the falls clinic, and how effective is that going to be? So we did this, and then we decided to look for a way we could transform this data so that we could communicate to operational leaders a little bit better. And the number we hit on was the number needed to treat. What people really want to know is, how many patients do I need to refer to the clinic to help one patient by preventing one fall revisit? And I think that we in the emergency department are pretty familiar with number needed to treat. And it's a good gut measure of how effective is this treatment, which allows us to compare this to other preventive interventions we may bring down the line. And critically, we have a pretty good ability to project this number needed to treat for our referral program, because we assume all patients above a certain risk threshold are referred. And we can look in that test data set and see which of those patients actually fell down. So we can figure out what the absolute risk of falling is among these patients. And then we know that we have a relative risk reduction from our intervention based on that old RCT I told you about. That's probably about 40%, 0.38 was the number we used. So if we say 10 patients flagged positive, 50% of whom in our test set went on to fall at a given threshold, we could say at that threshold, the number needed to treat is about 5.5 patients referred per fall prevented, which is really good. I would argue. I think referring 5 patients to prevent an ED visit is on the more effective side of interventions that we perform in medicine in general. And what we can do is transform a number ROC curve into a number needed to treat curve. And the way that we do that is we take every threshold from 0 to 1, and then using that threshold in the test data, we calculate which percentage of patients would be referred, and then what their absolute risk was, and we can calculate how effective the intervention would be. And as you would expect, if we just refer everybody, we have an intervention that's not super effective, right? The NNT is about 30, which you could start to get into arguments there that maybe it's not the best use of our resources to be referring 30 patients to a pretty fancy clinic to avoid one fall revisit. As we get down to how many patients we're looking to refer per week, though, we get into this idea of somewhere in the order of 10, a number needed to treat of about 10. This green spot represents if the model were perfect and only picked patients who would fall, the absolute risk was 100%. You're never going to get quite there, but it's nice to see where it is on the chart. So this was the curve that we were able to take to operational leaders and say, hey, we have this situation where we think we have an algorithm that's pretty effective in picking high-risk patients to send to the falls clinic. So that got us one step further. But it's another, oh great, now what moment, right? So now that we know we've got the algorithm kind of locked down, the question is, how do we move from this model to the predictive solution that I talked about earlier? And we have a couple steps that we need to go through. And I'll move a little bit faster on these steps. It's more about knowing that these things need to happen than getting into the nitty-gritty of how each one works. But basically, we need to operationalize this algorithm so it goes from working like on some research machine with a highly curated research data set to moving in real time when patients come to the emergency department. And then we need to design a clinical decision support workflow that puts that in front of providers the right way. And then critically, we need to get this thing approved by whoever it is lets us turn it on in the hospital, which at the start of this project was maybe a little bit nebulous. So first are the technical challenges. How do we get this thing to run in real time? And basically, most of this work is done on this curated research data set. Most hospitals have an operational reporting database that can be used for reporting that's refreshed every 24 hours. It's very similar to the research data sets. And then a transactional database that runs in real time that's a little bit harder to query. And the biggest takeaway from this is these models that we have, like this kitchen sink approach where we put 725 features into it, are really hard to run in an operational transactional database. The other problem with a model with 725 features is each one of those features you need to maintain. If we change the way that we chart something, then we've changed the inputs to our model. So when you think about the maintenance cost of the model, even though it's technically possible to do something that's very complicated, it's always a lot cheaper, easier, and much more robust against risk of like random changes happening to variables to use an operation, to use a more parsimonious approach. So the technical solution that we came upon was to use a secure cloud-based location to do our scoring. We can put the model that we chose, which was it's now a lasso regression-based model, up in this cloud. It pulls data variables from the transactional database and then returns the score as well as some metadata about that score to our electronic health record. We went from 700 to 20 features. And initially we took a little bit of a hit in our number needed to treat. We went from 10 to 12 among our 10 patients per 10 patients per week that we referred. We moved up to 10 patients per week to get 5 referrals filled at some point during the process. But then we continue to, look at this algorithm. We're actually back down to get towards that 10 number needed to treat just by some advances in the data science that we use as we've iterated this model over time. One critical issue here is we needed to retrain and revalidate the model in production data. So production data may look different from research data in a lot of small ways, the ways that variables are taken care of. And what we wanted to do, we did another retrospective test before this model went live, where we took years of retrospective data in the exact format operationally we were going to use our model in, and revalidate the model to make sure it still worked the way we thought it did. And if you don't do that, you can get some surprises. So this is just a graphical interface of how the model works. I try to avoid Epic jargon, but Hyperspace is the name of the Epic tool that we use. Like when people say I have Epic, what they're logging into is Hyperspace, which is the user interface that interacts with these databases. And what happens is when an older adult comes to the emergency department, they get put, data starts getting pulled from the transactional database, scores are predicted, and then those scores are used in Hyperspace to generate an alert when necessary. And if we look at the current model that's running, we can see like what are the values that drive those scores. And we've tinkered with this model a little bit, but one thing that we found is increasingly important because we tell providers what drove the model to make its decision, that we have a model that happens to have some face validity. And in this case, it does. If you look at the things that are important to falling, it's like if you use a cane or walker, if you've fallen in the past, how you get to the emergency department, whether by EMS or private vehicle, which is probably a proxy for a lot of access to healthcare or support that you have at home, how many ED visits you've had in the prior 180 days, different age brackets change things. These are all things that I would say, based on the falls literature, have a lot of face validity for clinicians. So once we've got the algorithm in real time and working, so now we can shoot scores back. The question is, how do we get them in front of clinicians? And this is where we entered a different phase in this project. We went from the data science phase, hospital data backbone phase, to the phase where we engaged our engineers. And the literature is riddled with clinical decision support tools that theoretically could change care. And that furthermore, when we survey clinicians or do something, people love this tool, but just because it works doesn't mean anybody actually uses it. Then it gets rolled out and nobody uses the tool or engages with it the way the designers thought. So it's really important for us to design a workflow that has usability and that engages providers so that they'll use the tool. And the way that we did this was we again went back to a conceptual model. And the model that we use, because it's one of the more popular models for human-computer interaction in healthcare, is the Systems Engineering Initiative for Patient Safety. And I was lucky enough to have research mentors who were well-versed in applying this from our Department of Industrial Engineering. And we thought about like, how do we very explicitly design a decision process that is going to take into account all the things that might throw it off. And that's the value for using one of these frameworks, is you're explicitly considering everything that you don't want to like come back a year later and be like, I can't believe I didn't think of this. So, we think about this proposed computer decision support tool, and we think about how this affects the people who need to use it, including patients, how it affects the flow of tasks in the emergency department, how the physical environment may affect it, and then organizational conditions like time pressure and regulation affect it. And looking at this graph is nice. How does that actually get to a process? Luckily, there's a lot of work out there in like, how do you take this and turn it into a set of human factors design steps to create your intervention? So there are a series of steps in which we analyze prior interventions, we talk to our clinicians to get input, we have interdisciplinary design sessions with users, we incorporate patient feedback, and then we do a lot of pre-production testing. It looks nice in a bulleted list. Once you actually like start to do it, you do a little bit more in parallel. This is from our publication on the design of the intervention, where you look at what we had was this, we had this initial concept that we wanted to use. We go through a series of collaborative design sessions where we talk to all the stakeholders about like the perfect world. Then we start trying to build it and test it, and it gets shot down over and over again. And we iterate on that design until we have something that's passing this user testing while maintaining the heuristics that we think are important from these collaborative design sessions, and then we're ready to launch. And the way the intervention works now is a patient arrives in the emergency department, and algorithmic screening is performed through that cloud-based location. As I talked about, variables are shot off in the background. The patient is assessed by specific rules for eligibility for the intervention. So this is, they have to be older than 65. They have to be marked for discharge in the emergency department, and they have to have a UW primary doc. If the patient is high risk for the week, because we can change this threshold, a CDS alert fires. It alerts the provider prior to discharge. It pops up in their discharge navigator. So in between when you enter discharge instructions and when you click the ready to go button, you'll see this big yellow screen that says the falls, the ED falls intervention has assessed that this patient is likely high risk for falls. Click on this link to see which particular risk factors brought them here. Do you want to send them to the falls clinic? And if the physician clicked yes, I do, a referral is made to the falls clinic and orders automatically placed. Referral information is added to the patient's after visit summary and verbally explained to the patient by nurses. And then the falls clinic schedulers call the patient the next few days to try to get something set up in this clinic. If the physician says like, no, I don't think it's a good idea, or I talk to the patient, they don't think it's a good idea, they can decline this and the patient gets usual care. So this schema went live now probably 15 months ago at UW and has been running since then. And when it went live and towards live, we made another shift from this world of like, so initially we're in the world of data science, and then we get moved into the world of engineering. And then the next world is the world of hospital quality and administration. And it's very similar to the engineering world. And in fact, people who are experts are often experts in both, but there's a whole different set of jargon and, a different way of looking at the world that I think when you're talking to a hospital quality director versus somebody who's a professor in an industrial engineering department, that it's important to have that context. And specifically, when we talk about these theoretical frameworks, there are a couple of very pervasive frameworks in hospital quality that it can be valuable to put these informatics assessments into. When you talk about a new informatics initiative, it always has this, like look of being something that's very cutting edge technology, high risk, high reward, kind of outside the usual what we do. So it's valuable to put it back into, we put interventions like this that don't use an AI model in all the time in the hospitals. And what we do often is this framework of plan, do, study, act, or plan, do, check, act cycles. The framework like this that's used at UW is this focus, plan, do, check, act cycle. And what we did was we took that last stage of intervention design and maneuvered it into this very explicit plan, to check, act cycle to say, this is how we're going to start it, this is how we're going to govern it, and this is how we're going to make it better. And that was a big sell for us when we talked to the approval bodies at the hospital. If you see the link here, if anyone's interested, we also have a toolkit for taking a predictive solution and moving it in through like a plan, do, study, act cycle, and how to run that at a hospital. So our final stage in my last 5 minutes here is this idea of approval and regulatory concerns. So once we have this and it's ready to go, how do you actually turn it on in your hospital? Like, who is it who says it's okay? And one of the first questions is it the FDA? Which is a more complicated question than it sounds like. The FDA does exert guidance over artificial intelligence or, decision support information systems, I think is the word that they use, which are occasionally classified as medical devices. Now, I've never gotten a medical device approved, but I assume it takes a lot of paperwork. So this was something we wanted to avoid. The FDA's guidance suggests that if you have something that tells patients, that tells providers that patients do or don't have a condition, it's a medical device. If it just tells them that, or if it automates some care process, like it automatically refers them, then it's a medical device. There is a bit of a carve out where if it's a decision support tool and it provides a provider with the ability to, quote, review the individual basis for the recommendation. So not just like, this is how we make these recommendations, these are the rules, but to say your patient is likely to fall because they use a cane and they're older and they've been to the hospital 9 times in the past 6 weeks, then you're not black boxing it. You're not just saying to the provider, like, this is what the device thinks. Then you have an information support system that is not classified by the FDA as requiring an IND or a medical device approval. So we thought about it, but we did not end up going down like an FDA approval. And I would encourage anyone else working on these types of things, giving the provider the individual basis is just a good thing to do. Like it's not a good way to it's good that the FDA doesn't regulate things that do that, but it's also good to do that whether you were worried about FDA regulation or not. It increases trust with the providers, and it makes the whole process work better in both in theory and in practice. Providers really like this ability to see why the model told them something. And then who is it who, within the hospital actually allows us to turn this on? At UW, we had a clinical decision support committee. This is a committee that reviews all CDS tools that are going live. And that was what initially approved this. And many hospitals have that, but I think around the same time, there's been a recognition at a lot of places, talking to other partner institutions, that there's a need for more institutional oversight of artificial intelligence solutions, and that maybe it's a slightly different body of people who can look at the risks, benefits, and governance of AI in healthcare, in addition to just the clinical decision support aspects of it. So this got me signed up for a new committee where we started a new AI committee to look at our use of ML and artificial intelligence in healthcare. And the really cool thing about this is at UW, we've been able to engage not just clinicians and not just technology experts on the healthcare side, but also some of our experts on the university side. So people who are, from DEI at our School of Medicine and Public Health, people who are experts in data science in our computer science and biostatistics departments, and then experts in ethics from our Department of Medical Ethics. And so we all sit on a committee which reviews any model that touches patients, and then we're able to ensure ongoing review and maintenance of these models. And this has just gotten off the ground in the past few years, and it allows us to enforce certain guiding principles. That would be one of my takeaways from this lecture is, when we're creating these predictive solutions, like, what is the bare minimum that we need to do to make sure that you would turn it on in a health system? And this goes back through some of the stuff that I've already talked about, but one is validating the performance. These are the predicting models at UW, is validating its performance in your own health system. Just because it works at one place is no guarantee that it works at another. So you need to evaluate on production data before you turn it live, or you can get burned. 2, that evaluation needs to include the relevant statistical measures, not just like, oh, it's got an ROC curve with a 0.78 area. You need to know, like, what are the relevant operational and health metrics, and how will this model change it? I'm not saying it has to be this NNT thing that we did, but at UW we make people take it to that next projected level, that this is how we expect this to influence patient care, and this is how we can measure it going forward. We ensure that the model output is actionable by following these 5 rights of decision support, and is created to not just provide output, but to help the users do something that's good for patients. We ensure that models are monitored after they've been run on the same set of metrics that they were initially tested on to make sure things aren't changing. And then we ensure that we have, top to bottom, a review of our basic healthcare ethics, as I had alluded to before. And it's a little bit out of scope here, but there are a lot of ways that these models can incorporate biases, and we want to be thinking proactively to prevent that from the beginning. Okay, so the next steps are, does this thing actually stop patients from falling at UW? We're in the middle of measuring and improving our appointment completion rates, and we're recently funded for this hybrid implementation effectiveness trial to move this out to 2 additional sites within our health system. So hopefully I'll be able to get back to you with some harder data on how well this has actually worked. We know that we are getting our referral metrics right now, and then in the past few months, it's been, how do we increase to make sure we're making the appropriate number of referrals, which we're doing well. With COVID has slowed us down a little bit, but so far the rates of patients getting referred actually showing up in Falls Clinic has been lower than we'd like. So we're now engaged in a series of interventions to try to improve that end of things. And hopefully I'll be reporting back to you soon on the success of that. So thank you for your time. I can stop sharing and take any questions. I do want to acknowledge the huge team of people who've helped me in this. I've used a lot of, as we've moved through here, it's been a truly large and multidisciplinary team that's partaken in this work, and couldn't have been done without the efforts of everybody on this list and many others.
Dr. Patterson, that was amazing. That was really great. Can you hear me now? Just making sure.
Yes, thank you.
There were some people who wanted to comment. Dr. Coletti?
Dr. Patterson, thank you so much for that very informative talk. It really fits within our mission and vision right now with both informatics, AI, machine learning, and geriatrics. So it's very much appreciated and very timely.
Dr. Beloya?
Hey, thank you so much, Dr. Patterson, for coming to give rounds to the emergency department. So I'm the research chair, and I also love geriatrics. So this talk was meant for me. I was asking Belam Konda who invited you, because it was so perfect. So thank you so much again. Our department is going through learning how to better provide care for older people. So this is just a fantastic example of how we can integrate our knowledge, the science, into the clinical care. So I think it's great how to use data to create these automated tools. I have 2 questions for you. One is, how scalable you think this is for other emergency departments, and what are the challenges when you're trying to basically, let's say Mayo wants to do or want to adapt this algorithm, kind of what challenges you see there? And then the second one is and I think you mentioned a little bit about how do you keep up to date? How do you continue to update this system? Does it on itself, or you wait for 2 years, you reassess, and then you intervene? Because we have had also, some issues with alert fatigue. And I know you mentioned briefly, you felt 10 people referral was a good goal. So basically it's those 2 questions. One is scalable for other EDs. And the second is the updating, keeping up to date with the system.
So both excellent questions. So first of all, in terms of scalability, I think that I'm hopeful that it's quite scalable. So there is some basic sort of data science backbone that a hospital needs to have to be able to put in these types of alerts, but it's not as much. It's not like you have to be like you guys already are a cutting edge center. So I've spoken with people, but you don't have to be to necessarily put this together. It doesn't need to be a tertiary care medical center that has employee data scientists, right? That helps at least early. It is important that you have enough resources that you can test a model in your own data, I think, to some extent before you're going to put it live. But none of the stuff that we do to run this model, especially because it only uses discrete data, is all that difficult to imagine recreating. You do need to be able to go back and get a big set of retrospective data. And there's no guarantee, as I said, that this particular model that we've trained is going to have the same metrics for you guys, for instance, as it would for us. But it's probably going to be pretty close, because we chose variables that have high face validity. And if not, as I said, like the actual training of the model or retraining is less work around this than the usability workflow issues. And I'm hopeful that, and we'll see as we kind of like move this out to other places, that those harder things to do, like designing the intervention around this, are more scalable, right? Because there's no reason to suspect that this idea of alerting the provider right before that they leave, that's not going to work at other places. You do need to have some place to send the patients, right? We were lucky at UW that we happened to have a falls clinic. It was like, yeah, we'd love to see them. Most places, I would imagine between the hospital system and the community, like there are falls prevention resources out there. And so it doesn't necessarily need to be this Cadillac intervention of, like a multi-D one-time clinic visit. Like you could imagine like a community-based falls program. And in that case, maybe you don't need as much of a number needed to treat. Maybe we set the threshold a little lower, refer more patients, send them to a community-based falls prevention program. So I would think it is scalable. And in fact, it's probably could be improved in various ways. Like if you look at different, everybody's got like a slightly different site, but there's no reason this concept couldn't be extended to say like, what resources do I have on the ground here? And that's what I want to connect patients with. And using this same approach, we have these like toolkits available to start to calculate the numbers needed to treat, to put it into that, PDCA design cycle. And then the technical aspects aren't there's no major barriers to reproducing them. In terms of maintenance, it's a great question. The system is not like an auto learning system in terms of like, it doesn't update itself. When you put one of these systems in, you do need to be careful that it's like, if I'm going to pull 10 variables from the system, I want somebody to alert me if one of those 10 variables changes. For instance, we had we had a sepsis alert at UW that, we validated it's providing well, and we had an Epic update, and suddenly the way that, all our antibiotics, everything that came in an IV piggyback, right, stopped being ordered as a single order and started being ordered as low. I was like, I'm giving ceftriaxone plus 125 mLs of saline. So one of the features in the sepsis model was how many boluses of normal saline of crystalloid do you get, right? Which is a good feature. But suddenly everybody was septic because it all had like 9, like you can't get into a hospital without a bunch of like IV piggybacks, right? So suddenly everybody's getting like 9 boluses of saline. So we had to switch the model up, revalidate it, and look at like total mLs of crystalloid that were given as opposed to number of boluses. So those types of little things can trip a model up, and it's important to keep up on them. And then what we do is sort of an iterative approach where like, yeah, in terms of, I think we've been running it every couple months, we'll take a look and make sure the model still seems to be fitting the data. There's this concept we talk about in these models known as data drift, where that association that you find exists for a certain period of time and then slowly drifts away as the pattern by which variables are accreted in the system changes. And that's some degree of data drift is inevitable. Like your model will never work as well as the first day that it was implemented. And it certainly, there's a lot of work in the informatics and in the computer science world about like specific strategies for fixing and preventing this.
Thank you very much.
Dr. Stanich.
Hi there. Thank you. I'm focused in geriatrics in our emergency department, and I love the idea of finding more ways to tackle our highest risk patients, truly. And so I have 2 questions. One is, do you see an element of this machine learning being able to take over screening? We're screening people for delirium and finding that they're very high risk, even for fall. We assess them for risk of fall. Do we think that the machine learning, it should be better, right? Because we're taking in more variables, but do we see it replacing screening?
So I think that like the biggest problem in geriatric screening right now is we think about moving from tertiary care centers that are doing all this stuff for older adults and are getting geriatric certified to like, what can we get out there in larger EDs across the country? I would say is identifying the highest risk subpopulations for screening, right? If we think about geriatrics, as I talked about that sort of public health slide, there's so many good things we could be doing that that screening for all of them is really tough, right? Like you could take a 30-year-old and you could, okay, we'll do the quick alcohol, the quick, domestic abuse, like a couple high yield screens, but in geriatric emergency departments, in some of these models, patients get 20, 30 minutes of screening for every older adult patient. The question is, do we want to devote more resources to screening, or do we want to find some way of screening these patients that's more efficient? And I don't think machine learning is ever going to replace certain focused screening questions. It's just hard to imagine. Like delirium, talking to a patient and doing a high quality delirium screen is not going to be recreated by a bunch of variables that were pre-existing in their condition, because delirium is an acute condition. But I'm hopeful that we can think about ways that we could use machine learning to identify high risk subgroups, because I think it's a much easier ask for people to say, hey, we're running these algorithms in the background, and certain people are going to be high risk for certain geriatric syndromes that need to be screened for, as opposed to trying to screen every older adult for every geriatric syndrome, which is going to be really tough and low yield. Also, there's been, as I'm sure some work around these geriatric screeners that are sort of more global, who's a higher risk older adult versus a lower risk older adult. I think there's a lot of promise there. But again, here's a place where machine learning could potentially fine tune it a little more for who's high risk for what specifically. I think we can at least leverage that data to improve the process.
Yeah, I totally appreciate what you're saying. The other comment I had was, we've talked about referring our patients to our Geri clinic, and they basically gave us the exact same concern, which was, oh no, you're going to send hundreds of patients to us. You'll overwhelm our fellows. We won't be able to do all these consults. I wonder, do you think that your algorithm could be applied to the visit in time, and then the resources you talk about, PT, I think about social work, and if you're a geriatric accredited emergency department, you essentially have a geri nurse that's a case manager right there. Do you think that you could replicate what's happening in the Falls Clinic during the 6-hour stay?
Hopefully, and I think there's been, when we started this, Falls Clinic was a convenient way for us to focus on the informatics aspect of this. And in the meantime, there's been a lot of work done in geriatric emergency medicine on focus assessments that happen in the ED. So there's nothing saying we have to have somebody called a few weeks later. In fact, it might be better to choose patients who are high risk. If you look at the gap care intervention for Falls, which is a PT visit on the way out of the ED, I think there's certainly reasons to be very hopeful for some of these short focused interventions that happen in the ED time. I think that this could pair well with that.
Well, thank you so much, Dr. Patterson. Clearly, your talk was very engaging. It hits on a lot of topics that our practice, research, AI, future ED planning groups are interested in. Because of time, I'm going to have people curate questions to me, and I'll connect them with you via email, if that's okay.
Well, thanks so much. Thank you for the opportunity to speak. This is a great group.
That was Dr. Brian Patterson. He is an exceptionally gifted speaker, and you should consider having him challenge your department like he did ours to think about the future differently than we think about the present. If you want to connect with Dr. Patterson, you can hit him up on Twitter at bpattersonmd, or you can connect with the show and we get your messages to him. Speaking of connecting with the show, I hope you enjoyed it and you're inspired. If you are, make sure you like, subscribe, comment on whatever platform you're using, and don't hesitate to reach out to us at alwaysonem@gmail.com or at alwaysonem through Twitter. We did just open an Instagram account, and we will be trying to advertise our content there as well. Thank you so much for listening. Until next time, keep on rising.
The Always On EM Podcast.
Emergency Medicine Grand Rounds.